1,500 meters below the surface, researchers followed the world's largest brains through a world of darkness, until one AI algorithm sifted 50,000 hours of whale clicks and spotted a pattern no human had ever glimpsed. The official story was that sperm whales were mysteries, but this technology suddenly began predicting their next sounds, hinting at structure where we expected chaos. The scientists' shock was just beginning, because what the AI revealed about whale communication would shatter everything they thought they knew. How could a machine decode a language nature had hidden for millions of years? Sound moves through seawater at nearly 1,500 meters per second, 4 times faster than in air. For sperm whales, vision fades to black long before their world even begins. At depths where sunlight dies, their eyes are useless, but their brains, weighing up to 8 or even 9 kilograms, the largest of any animal on Earth, are built for another sense entirely. Every click that leaves a whale's head is a pulse of energy, a flashlight made of sound. These pulses ricochet through the gloom, bouncing off squid, rocks, even distant whales, returning as echoes that paint the ocean in detail no human eye could ever match. Researchers on deck listen to the ocean's hidden conversations, knowing that each click is more than noise. It is the currency of survival. A single coda, a rapid-fire burst of clicks, travels for tens, sometimes hundreds of kilometers. Out here, a whale can detect a rival or a family member long before any shape appears in the water. Biologists describe sperm whales as living inside a 3-dimensional map drawn entirely from echoes. In these depths, sound is not just a tool, it is sight, memory, and connection. The anatomy behind this is staggering. Inside a sperm whale's massive head, the spermaceti organ focuses and amplifies clicks, turning the animal into a living sonar array. The lower jaw receives returning echoes, channeling them to the brain. With each pulse, the whale scans the world ahead, mapping prey and kin in total darkness. These clicks are not random. They are precisely timed, shaped by muscles and air sacs, modulated in rhythm and intensity. For a whale, a single click can mean the difference between finding food and missing a meal, between reuniting with family or drifting alone. Scientists have measured these signals traveling unbroken for over 100 kilometers. In the open ocean, where groups can be separated by miles of water, the ability to send and receive codas becomes a lifeline. It is not just about hunting, it is about keeping track of who is out there, which clan is nearby, and whether a calf is safe. The whale's brains process these layers of sound in ways we are only beginning to imagine. Decades of research suggest their acoustic world is as rich and nuanced as our own visual one. For the field teams, this is the foundation of every question they ask. Why do these animals invest so much energy in sound? Why does a sperm whale need a brain 3 times the size of ours? Every answer points back to the same reality. In the deep ocean, sound is everything, and silence is blindness. Before any algorithm can decode a single pattern, before any AI can predict the next click, scientists must first understand what it means to live in a world where silence is blindness, and every sound is a thread connecting lives across the abyss. 50,000 hours of ocean recordings, each second packed with the rapid-fire codas of sperm whales, waited in digital silence. The archive, built over decades by teams in Dominica, was more than a collection. It was a living record of every click, every call, every hidden conversation echoing through the deep. The challenge was clear. No human ear or mind could hope to sift through the sheer scale of this data. The solution arrived in Code, a transformer model built to find order in what once seemed random. Ours was no longer a barrier, it was a resource. The AI team began with raw hydrophone tracks, slicing them into individual click sequences. Each coda was mapped as a string of digital tokens, preserving the rhythm and timing whales had shaped over millions of years. Spectrograms lined the lab walls, their jagged patterns hinting at structure beneath the chaos. The tokenization pipeline became the backbone of the project, converting sound into a language the algorithm could learn. Every token represented not just a click, but a potential building block of meaning. Tokenization became the workbench of discovery. As the model trained, it faced a test. Could it predict the next click in a sequence it had never seen? The team held their breath each time the algorithm ran on held-out data, sessions set aside to prevent overfitting. The results flashed across the screen. The model's top 1 accuracy on unseen codas far exceeded chance, proving the clicks were not just noise. They followed rules, patterns and structures that pointed to a hidden grammar. One engineer, watching the prediction curve climb, whispered that they were seeing order where they had only expected chaos. Metrics became the new currency of trust. Cross-validation folds confirmed the findings. The AI could forecast the next click with a precision no human could match. The lead specialist summarized it in a single line. Next click accuracy was well above random. For the first time, the archive's scale was not a barrier, but a window into a world of structured sound. Accuracy opened the door, but not everyone was ready to call it language. The lead linguist, reviewing the output, cautioned the team. Patterns, yes. Structure, undeniably. But meaning remained out of reach. She said they could see the skeleton, but they did not know what the flesh looked like. The AI had revealed the architecture, recurring units, rhythm, rubato, even ornamentation, but the true intent behind each coda was still locked away in the deep. Skeleton was visible, but the story was not yet told. The team pressed on, knowing that every answer raised new questions about what it means to communicate in a world built from sound. They moved forward with curiosity and with a growing sense of urgency. Long before any AI model tried to parse their codes, scientists in Dominica tracked the same families of sperm whales year after year. Each encounter began with a familiar rhythm, bursts of clicks always in the same pattern, echoing through the water like a signature. These codas, as biologists call them, are not just random sounds. They cluster by family and by clan. Over decades, researchers have mapped these acoustic fingerprints across generations, finding that a calf born into a matrilineal group inherits not only its mother's company, but her dialect, a unique set of codas that stays with the family for life. Photo identification and genetic records built the backbone of this acoustic research. Scientists matched fluke patterns and DNA samples to individual whales, then overlaid years of sound recordings. The result was unmistakable. Families share nearly identical repertoires, with subtle variations marking the difference between neighboring clans. In the Eastern Caribbean, the so-called 1+1+3 coda, 1 click, pause, 1 click, pause, 3 clicks, became a calling card for an entire region. Machine learning models, trained on tens of thousands of these sequences, could classify clan dialects with over 95% accuracy. The same patterns echoed back and forth, season after season. But the story deepens when you watch a calf learning to speak. Field teams documented young whales spending up to 10 years in apprenticeship, shadowing mothers and aunts, practicing their clicks in long, playful exchanges. Early attempts are clumsy, timing off, intervals too wide or too tight. But over time, the juvenile's codas converge on the family dialect. By age 8 or 9, a calf's acoustic signature matches its mother's with nearly 90% fidelity. It is not just mimicry. It is cultural transmission, a process as rich and slow as a human child learning the rhythms of its own household. Linguists reviewing these records describe the whale's vocal culture as layered and resilient. Codas persist through generations, even as individuals come and go. Each matriline carries its own legacy, woven into the fabric of the clan's soundscape. When AI models cluster these codas, the boundaries between families are as clear as borders drawn on a map. The whales know these differences instinctively. To them, a single pattern can mean kinship, history, or belonging. This continuity is not just a curiosity, it is a lifeline. In a world where sight fails and distances stretch for miles, the ability to recognize a family's voice anchors every whale to its place in the ocean. The evidence is overwhelming. Sperm whale society is built on sound, passed from mother to calf, year after year. Every click, every rhythm, is a thread that ties one generation to the next. On a windless morning off Dominica, the research deck fell silent as the team prepared a new kind of experiment. Engineers checked every connection on the hydrophone array, eyes darting between laptops and the open sea. The AI model, trained on tens of thousands of hours of whale codas, was about to broadcast a synthetic sequence, an imitation built from patterns no human could parse. The lead scientist's voice trembled as she called out the final checklist, her hand hovering over the transmitter. Years of careful observation had led to this, a controlled emission designed not to disrupt, but to echo the rhythms the whales themselves used. The signal pulsed through the water, a string of clicks shaped by the AI's analysis of clan dialects and timing. On the monitors, the real-time hydrophone feed lit up with the ocean's response, every frequency mapped in color. For a moment, nothing happened. Then a new set of codas appeared, distinct from the background, matching the family signature identified in previous drone-tagged encounters. Crew members crowded around the screens, breath held as the incoming clicks grew louder and more complex. Someone whispered, "That's them." The team watched as a pod altered course, moving steadily toward the array. The data stream showed a clear shift. The whale's codas increased in tempo, their interclick intervals tightening with each pass. One biologist's hands shook as she logged the timestamps, her voice barely steady. The lead technician read out the signal-to-noise ratio, confirming the clicks were not echoes or artifacts. They were intentional responses, layered atop the synthetic sequence. The deck protocol demanded silence, but the tension was electric. Every person on board knew this was no routine playback. It was the first time the AI's output had been met with a measurable, real-time reply. Session after session, the pattern held. Across multiple days and deployments, the whales responded to the codas generated by the AI in nearly 7 out of 10 trials. The aggregate response rate, 68%, stood out against the baseline of natural encounters. Analysts pored over the logs, comparing approach vectors and acoustic profiles, searching for any sign of anomaly or stress. The findings were consistent. Whales approached the source, circled, and exchanged codas before fading back into the blue. No one could say for certain what those clicks meant, but the two-way engagement was undeniable. As the sun set, the team gathered around the data displays, replaying the sequences on loop. The lead scientist's voice, still shaking, summed up what everyone felt. We're not just listening anymore. We're part of the conversation. If you're already speechless about what scientists witnessed, like and subscribe to Stellar Insights 42 right now. In the shadow of cargo ships, the ocean's voice fractures. Shipping lanes, once blank stretches of blue, have become corridors of relentless mechanical thunder. Hydrophone logs capture the evidence. Where a mother's coda once rang clear for miles, the signal now drowns in a wall of low-frequency engine noise. Analysts measure the damage in ratios, signal to noise, and click to chaos. Sometimes the coda vanishes entirely, lost beneath the churn of propellers. One session stands out in the records. A juvenile, tagged and tracked, attempts to follow its family's acoustic trail through a busy shipping corridor. The calf's clicks scatter, bouncing back with no clear answer. The mother's call, usually a beacon in the dark, is masked by the roar of passing tankers. Surface observers log the moment. The calf veers off course, swimming in widening circles, pausing, then calling again. Minutes stretch into an hour. The family's codas blur into background noise. For that span of time, the juvenile is alone in a world gone silent. Researchers reviewing the spectrograms see the pattern repeated. Codas clipped short, intervals stretched, calls layered atop the low hum of ships. In some recordings, the whales fall quiet, as if waiting for the noise to pass. The data leaves little room for doubt. This is not a distant threat or an abstract harm. The masking is immediate, personal, and measurable. Every decibel of engine noise chips away at the threads that hold these families together. For the scientists, the evidence is inescapable. The ocean's oldest conversations are being silenced, not by nature, but by us. Acoustic records from oceans around the world reveal a troubling pattern. In the Atlantic, Pacific, and Indian Oceans, researchers have logged thousands of coda sequences, some familiar and others jarringly different. What once were rich, layered click patterns now sometimes collapse into short, flat bursts. Teams in Dominica, New Zealand, and Japan compare notes and find the same trend. In high-traffic shipping corridors, the complexity of whale codas drops. One analyst in the North Pacific flagged a cluster of recordings where the usual rhythms were replaced by stripped-down, repetitive clicks, codas so stark they barely resembled clan dialects. The timing and tone suggest a shift, not just in how whales communicate, but in what they are trying to say. Meanwhile, orca researchers track a surge of ship interactions off Spain and Portugal. Over 100 incidents since 2020 show orcas targeting rudders, sometimes in groups, often repeating the same maneuvers. Hydrophone logs capture bursts of synchronized whistles and clicks before these events, but no direct evidence links these to sperm whale codas. Still, the parallel is hard to ignore. Across species, the ocean's largest mammals are changing their behavior in noisy, crowded waters. Policy teams sift through the data and propose urgent measures. Ideas range from slow speed zones and rerouted shipping lanes to hull designs that dampen noise by several decibels. The International Whaling Commission calls for global acoustic sanctuaries, warning that without action, the world's cetacean cultures could fragment beyond repair. One Project CETI scientist, Voice Raw from Fieldwork, puts it bluntly: "We're watching the ocean's grammar unravel. If you want to hear what comes next, you have to decide. Do we quiet the seas, or let these voices fade? Do not miss the moment the world chooses." Like and subscribe to Stellar Insights 42 now. Right now, our oceans are louder than ever. Commercial shipping noise has doubled every decade since the 1950s, masking the voices of the largest brains on Earth. As AI finally lets us listen, what we choose to do next matters. The future of whale communication depends on whether we value silence enough to give it back. Their survival and our own understanding hang in the balance. Share your thoughts below.